Hi, I am Praveen Raj, Assistant Professor of Mechanical Engineering Department at Jyoti Engineering College, Tirur. Today, I am going to discuss with you an important topic from engineering mechanics, which is the work energy principle. Okay, so basically, we know the definition for work and energy. Now, how we can relate that work and energy? That is what is discussing in the principle. Okay, and we know that the work done by a force, the work done by a force is the force times its displacement. And according to that work energy principle, what it states is that the work done by an object, the work done on an object is equal to its change in the kinetic energy. Okay, so that is a simple definition for work energy principle. Work done on an object is equal to its change in kinetic energy. That is, in mathematical form, it is W is equal to delta K, where W is the work done on the object, and that is expressed in joules, and delta K is the change in kinetic energy, that is also expressed in joules. And the change in kinetic energy is nothing but it is the final kinetic energy minus its initial kinetic energy. Now let us see how we can prove this work energy principle. Okay, and from the definition we know that the work done on an object by the net force is equal to change in its kinetic energy, and mathematically we have expressed that as work is equal to work done on the object is equal to delta K. And from the definition of the work we know that W is equal to force into displacement. And we know that what is a force, and by Newton's second law the force is defined as mathematically it is defined as mass times its acceleration. So work can be written as mass into acceleration again into the displacement. Okay, and we rewrite the term displacement s in terms of its final velocity and initial velocity. So we uh, know from the uh, kinematic equations. Okay, kinematic equations of one-dimensional motion. We have the expression 2as is equal to v square minus u square, or the final velocity square minus initial velocity square. Okay, so from that we can write the expression for displacement in terms of velocity as s is equal to vf square minus vi square divided by 2a. So substituting that value here, it gives work is equal to ma into vf square minus vi square divided by 2a, and this a cancels. So the remaining term is w is equal to half m into vf square minus vi square. And from the definition of the kinetic energy, mathematically the kinetic energy can be expressed as it is equal to half mv square, and this half m into vf square represents the body's final kinetic energy. So work done can be expressed as work done is equal to half mvf square is kinetic energy final minus half mvi square is kinetic energy initial. So W is equal to, or F into S is equal to half M into Vf square minus Vi square. So that represents the work energy principle. So this is an important topic as far as an exam point of view. This is an important topic in engineering mechanics. So we can do some one simple problem from this work energy equation. So from a connected body system, how we can use this work energy principle for calculating the displacement or velocity. So that can be discussed in a simple problem. Okay, let us see the problem. So here the question is, determine the constant force P that will give the system of bodies shown in the figure a velocity of 3 meter per second after moving 4.5 meter from a rest. So take mu is equal to zero point 0.3 and the pulleys are small. So it is a connected body system consisting of three different blocks. And let us see what are the given data. So in the question it is given that the system starts from rest. So its initial velocity is 0 and it attains a velocity of 3 meter per second. So its final velocity is 3 meter per second after moving 4.5 meters. So the distance covered or displacement of the body uh, uh, when the velocity changes, it is 4.5 meters. Now let us see how the free body diagram of the system can be drawn. Okay. Now from the figure, it is clear that the displacement of all the blocks will be same, and similarly the velocity of the three blocks also remains same when we apply a force at the first block. Okay, so when we are taking the first block, force P is applied in this direction, and its weight is 250 Newton is acting in the downward direction, and the normal reaction on the horizontal surface is marked here. And since the block is moving towards left side, the frictional force is acting towards the right side. And we know that there is no movement for the block in the upward direction. So sigma F is equal sigma Fy equal to 0 in the first case. So from that we will get N1 is equal to 250 Newton. And the frictional force, we know that it is mu into N1, which is 0.3 times the normal reaction, which is 75 Newton. Now similarly, when we are drawing the free body diagram of the second block, we know that its weight is acting in the vertically downward direction, so that we can resolve the weight into two components. One is perpendicular to the plane and other one is parallel to the plane. And the component perpendicular to the plane is 1000 into cos theta. And cos theta we can find out from the data given in the question. And the component parallel to the plane in the downward direction is the 1000 sine theta. And since this is an inclined plane, this normal reaction N2 will be perpendicular to the inclined plane. Okay. Now, again, we know that this block is moving in the upward direction. So, the frictional force at the second plane is acting in the downward direction, which is equal to mu into N2. Okay. Now, here also, when we equate the uh, uh, forces perpendicular to the plane to 0, we will get N2 is equal to the vertical component of the weight. So the the component perpendicular to the plane of the weight is 1000 into cos theta, and from the figure it is cos theta is 3 by 5. So N2 will be equal to 600 Newton, and from that we will get the frictional force on the second plane is mu into N2. So which is 600 times 0.3. Okay, so which is equal to 180 Newton. And similarly, the free body diagram of the third block. So free body diagram of the third block will give N3 is equal to 500 Newton and F3 is equal to mu into 500, which is 150. Now we know that the force P is a constant which is applied at the first block. And if we write the work energy equation for the entire system, from the definition of the work energy equation, we know that work done on the body is equal to change in its kinetic energy. So F into S, work done is force into displacement. So here towards left side, the entire system moves. That means you need to consider any force acting towards left side as a positive force. So any force acting in the direction of motion is considered to be a positive force. So keeping that in mind, if you write the net force acting in the system, it will be P minus F1. Here it is opposite force. That F2 is another opposite force. So minus F2. Then the component of weight parallel to the plane, which is minus 1000 sine theta. Then minus F3. So this is the net force acting in the system. So net force into the displacement. So due to this force, it is go its displacement is S. Okay, so force into the displacement S is equal to half into the total mass. Total mass is W1, W2, and W3 are the weights of each block. So the total mass is W1 plus W2 plus W3 divided by G. So half into that value into v square minus u square, and its final velocity is 3 and its initial velocity is 0 since it starts from rest. So substituting this value, we will get the force required to move the block is 1383.39 Newton. So this is how we are applying this work energy equation for solving the connected body system problem. So whenever in a question, if we can relate the force, displacement, and velocity, we can easily solve that problem by using the work energy equation. So based upon the data given in the question, you can solve the problem either by the work energy equation or by the impulse momentum equation or by the D'Alembert. So depending upon the data given, you can use the uh, suitable methods for solving these kind of problems. So I hope that this problem is clear to everyone. So we'll be meeting with another video in the next. Thank, thank you.